Okay, folks, welcome to this second vodcast. It's an extension of that previous one. It's specifically targeted at projectile motion. Now, there's a comment there that it's unlikely to feature as prominently as it used to. What do I mean by that? Check this out. This is the old study design, vector calculus. There was a bunch of dot points, including studying motion along a path in 2 or 3 dimensions, and such examples as you see below. Now, the current study design that came out a couple of years ago has differentiation, anti-differentiation of a vector function with respect to time, and applying vector calculus to motion in a plane. So they're actually specifying motion in a plane, including projectile and circular motion, which suggests two-dimensional motion rather than 3 dimensions. So this is one area where life for you guys should be a bit simpler than what it was before. Okay, so what is projectile motion? Well, it's the study of the motion of an object projected or thrust into the air, not necessarily perfectly vertically as we were doing in the kinematic study, but with an angle of projection to the horizontal. It's normally in a situation where air resistance is disregarded, but it can come to play as well. And some other situations, that object is normally idealized down to a single point, thought of its center of mass, the particle has no spin. There's some other assumptions that play, but that is essentially what projectile motion is all about. Okay, so there's the classic setup for projectile motion, ignoring air resistance as we're going to do for a while. We've got our acceleration due to gravity, g, working in the negative j direction. As you can see, negative 9.8 j is marking its acceleration. Capital V is marking the initial speed of projection, and theta is marking the angle of projection, the angle of elevation of its projection. So what we can do, here's our initial velocity vector, and we're breaking it down into its 2 components, our v cos theta in the I direction, our v sine theta in the j direction. So, and that gives us the velocity vector for t equals 0. Now, as time is going, it's of course, our position vector is changing, and it's moving along that path. Now, with air resistance ignored, that path will be parabolic. Okay, and eventually, at some point t, returns to the same height as its point of projection, commonly taken to be the ground level, but not always, as we'll see later. Okay, so there's some just key aspects of sorry, I'm just trying to, of our projectile motion. So acceleration is a function of time. We're looking at acceleration in a plane, has just the j component, negative gj, and velocity, of course, is the antiderivative of that. So if we antiderive that, and then we also appreciate that our initial velocity is given by that capital V for the initial speed of projection, theta for the angle of elevation. There's its 2 components as broken into the I's and J's. And when we put it all together, we get a generalized expression for velocity as a function of time. Okay. Now, some notes, of course. Instantaneous speed, as we recall, is just the magnitude of our velocity vector function. And the maximum height at which this particle will reach on its parabolic path will be when the j component of the velocity vector function. So here it is, our j component. Let me just get that pen working again. Our j component of the velocity vector function is equal to 0. Okay, when it's moving perfectly horizontally, that's when it's reached its maximum height. So we can set that to 0 and solve for t, and we can obtain the maximum height it reaches above the point of projection. So hopefully all that is nice and clear. Okay, so from our velocity vector function, we transition to the position vector function. So, of course, that's obtained through anti-differentiation. Now, in this particular instance, we're actually taking the point of projection to be at the origin. This need not be the case, but we're just going to assume it's the case for the point of view of just determining some generalized rules of what you could expect a position vector function to look like. So as we said before, it has a parabolic path. So if we let assign x to the function assigned to y and y to the function adjacent with j, we should be able to get a rule of y in terms of j that is a quadratic rule and matching that inverted parabolic path that it travels. Okay, this is all under the assumption of course, negligible air resistance and a point of projection being at the origin. Okay, now through the course of these last two slides, we've come up with generalized rules for velocity and for position. It's not advisable that you just memorize these and plug them into situations of projectile motion. Always understand how they're derived from the initial acceleration function as a function of time. It's simply a constant function in the j direction, negative g in the j direction, or negative 9.8 in the j direction, of course, in meters per second squared. All right, guys, let's test your understanding with this particular question. Now, just looking at it, I'm sure a lot of you who study physics will be able to think about solving it via constant acceleration formulas only, which is a valid means to go. But what I'd like you to do is test your skills in calculus and see if you can do it from the initial assumption that the acceleration vector function is simply minus gj, or minus 9.8j. So, and use calculus to derive the velocity vector function and position vector function, and to answer the questions that result using your skills and knowledge of calculus alone. Later on, we'll be looking at how this can be done with constant acceleration formulas, which is a bit simpler, but misses the understanding behind them as well. So anyway, have a go and come back and we'll go over the solutions. Okay, so here we go. We need to state the initial velocity vector of the ball. And of course, that's just taking our initial speed and splitting it into 35 cos 20i plus 35 sine 20j. It's as simple as that. Find the velocity of the ball as a function of time. There it is. There's our initial velocity, and there it is approximated. So how do we find our velocity vector as a function of time? Now in these solutions, it's appealed straight to the rule, but of course that's obtained simply from acceleration equals minus gt. So I might just, so acceleration as a function of time is equal to minus gj, just constant acceleration. And from there, we're able to establish the velocity vector function as a function of time by anti-differentiation. So hopefully you guys were onto that. Okay. All right, and there's its approximated values. Okay, from there we need to determine the maximum height the ball reaches and the location of the maximum height from the tee. So basically the x and y components of its maximum height, of the turning point of its parabolic path through the air. Okay, so as we said before, all we need to do is focus on the j component of our velocity vector function and set it equal to 0, because when it's traveling with a direction that's perfectly horizontal, we know it's reached its maximum height. So just to highlight, this is what we focus on, setting that equals to 0, and that determines when the ball has reached its maximum height. So hopefully you're able to see that. Okay, and the distance it's traveled in order to get there. So it's taken 1.225 seconds. So of course we then plug that into determine the maximum height it reaches, we need to obviously um, anti-derive our velocity vector function to come out with our acceleration vector, our position vector function. There it is, as you can see before you. Okay, and appreciating that it starts at the origin, the point of projection is at the origin. We come up with our generalized rule for a position vector function as approximated to 1 decimal point, as you can see there. And then we need to plug in 1.225 to those two components, and we get both its height, maximum height of 7.35, and the horizontal distance from the point of projection of 40.3. So hopefully you're across all of that. Okay, so that's part C. We've anti-derived our velocity vector function and then plugged in the time it takes to reach our maximum height into both components to work out its position when it hits that maximum height. Okay. Okay, find the time that the ball is in the air. I'm going to use my position vector function for this, and of course the time it takes to return to the ground, because the point of projection was fixed to the ground at the origin. It's when the time it takes, all I need to do is focus on the j component, and in my position vector function, when I set the j component to 0 and solve, that'll be the time when it returns to the ground, returns to the same height as the point of projection, which is on the ground. So solving that, setting that to 0 and solving gives us that particular time. So the ball's in air for 2.45 seconds. Now find the horizontal distance covered by the ball. Obviously I need to then take that 2.45 seconds approximately, sub it into the I component, and then that gives me my horizontal distance, as you can see. So I'll just get rid of this pen for a minute. Hang on, there's the horizontal distance. Plugging in that 2.5 gets me 80.6 meters as the range at which I hit the ball before it touched the ground for the first time. Now, it's quite an interesting observation here. We actually worked out the vertical height and the horizontal distance from the tee to the maximum height. I could have actually, with the appreciation that we're dealing with just with zero air resistance and just constant acceleration at play, just taken that horizontal distance and doubled it. So the previous answer was 40.3. I could have just realized it will double that distance, being a perfect parabolic path will take me to the total vertical or horizontal distance that the ball traveled. And the time that the ball is in the air, of course, I worked out previously that it was 1.225 seconds it took to reach the maximum height. If I would have just doubled that as well, I could have got an answer to D as well. So I could have answered D and E based on my previous calculations. But of course, be warned, take note, you can only do that when it's a situation of acceleration is due to gravity only, and there's no other factors at play, such as air resistance. All right, for those physics boffins in the room, they would have been throwing up their hands in disgust at such an inefficient way we were examining before for producing answers to problems, when we could have just gone straight to the formulas for constant acceleration. Why are we justified in doing this? Well, the only acceleration at play in this situation is acceleration due to gravity, working at 9.8 meters per second directly downwards, or in the j direction, in the negative j direction. And of course, there's zero acceleration working horizontally. So what can we do here? It means we can split this projectile motion, this two-dimensional motion, in two directions. One, we can treat it in the vertical direction, and we can treat it in the horizontal direction. So changes in the vertical direction could be described like this. Our initial velocity is our the initial speed, v, as broken into the vertical direction. So v times sine theta would be our initial velocity purely in the vertical direction. and our acceleration we encounter is minus g. Now with that in play, it opens the door for all kinds of questions we can answer using our constant acceleration formulas. Now, we can also appreciate that what's happening in the horizontal direction, there is no acceleration occurring horizontally. It's got zero acceleration. So it must be traveling with constant velocity. As we're ignoring air resistance, it's merely a situation of constant velocity. So in other words, if we resolve our initial speed of projection, v in the I direction, in the horizontal direction, it means it's traveling forever at that constant rate. So we could answer distance and time questions based on that fact alone. Okay, guys, let's just quickly re-examine that previous problem with the view of solving it via the formulas of constant acceleration. So if you can recall C, we had to determine the location of its maximum height above the ground, both in terms of the X and Y, the height it reached above the ground, and its horizontal location from the point of projection. And how could that be done using our formulas? Well, of course, if we resolve things vertically in the J direction, our initial speed becomes the speed of projection as resolved horizontally, so 35 sine 20, acceleration minus 9.8. And of course, we know its final velocity in the J direction will be equal to 0 once it's reached its maximum height. And we can just use our v squared equals u squared plus 2as, resolving for s, and we come up with that maximum height that it reaches above the ground. What about the horizontal distance that maximum height is from the point of projection? Well, we know it's traveling at a constant speed in the vertical direction of 35 cos 20. So the initial speed resolved horizontally is 35 cos 20. It's traveling at that constant speed horizontally. So all we need really is to multiply that by the time it takes to reach the maximum height. And then we can go back to our J direction thinking, and we need to, with setting V to 0, U to 35 sine 20, we're able to solve for t. So with V equals U plus AT. So V minus U divided by A gives us our time. It's roughly 1.22 seconds. And if it's traveling at that constant speed horizontally, it means that it's traveled a horizontal distance of 40.17 meters. So as you can see, the same values as we got before. Now, D and E, as we suggested last time, we could just simply, the time that the ball in the air will be, of course, double the time it takes to reach the maximum height, this being a situation of perfectly symmetrical parabolic travel through the air. It'll be double 1.2 is the time that the ball is in the air in total. And of course, the horizontal distance, the range, in other words, covered by the golf ball, well, of course, we could take the horizontal distance to reach the maximum height, and we could double that as well to talk about the range in which it's traveled. Okay, so really you can see we can simplify the process by using our formulas for constant acceleration. Okay, guys, we're going to finish off this vodcast on projectile motion with a couple of problems that should bring into relief the techniques, the two techniques we've been discussing so far. This is a nice problem because, of course, the point of projection is not equal to the origin, and we're fixing the origin at sea level, as you can see. So launching point and impact point are not at the same height, so you need to think about it. So it's leading you into the origin, of course, being directly below the cannon, as you can see from the initial position vector at 0i plus 50j. So directly below that, the cannon at sea level would be the origin. So have a go at it. See if you can use your skills in vector calculus to come up with an answer. I'd prefer you to use vector calculus rather than constant acceleration formulas here, particularly as A is immediately leading you into finding a position vector function. So might as well stick with vector calculus in this instance. In the second problem, you can choose whatever technique suits your particular learning style. Okay guys, let's go through the solution. So using the full blown mechanics of vector calculus, we start with our acceleration function. Only acceleration due to gravity is at play here. We anti-derive it for our velocity vector function. Now in this particular case, we're not given the speed of projection and the angle of projection. It's broken down into its component parts already for us, making it easy. So broken down into its horizontal part, 120i, and its vertical part, 50j. Okay, so obviously that gives rise to the constant vector c, which we return into our velocity vector v as a function of t, and we arrive at this. So that gives us a stepping stone to our final position vector function, which is ultimately what we need to find. Now moving on, of course, we anti-derive that velocity vector function with respect to time. We've got our d for our vector of our constant vector of anti-differentiation. Now it's not being projected from the origin in this particular instance. We've set our origin down at sea level here, so I might even just mark that. Here's our origin here. Okay, down at sea level, which will be convenient for later problem solving. So of course that gives rise to d being equal to that initial position vector, and then we put it back into our displacement as a function of time, or our position vector function, to arrive at our final answer, the answer that we needed to for part A. Okay. Now, from there we need to determine the height it reaches above sea level, the maximum height it reaches above sea level. And what can we do in terms of vector calculus? It means we can actually use the j component of our velocity vector function. So let's just grab a different color. So we go to this component. So remember, our velocity vector function drives direction, and when it's traveling perfectly horizontally, that means it's reached its maximum height. So we set that equal to 0 and solve it to find t, and then that's the time it takes to reach that maximum height. How do we work out the maximum height itself? And you guessed it, we can substitute that t value into the j component of our position vector function, and then we get the maximum height it reaches above sea level, as you can see, 177.55 meters. All right, what's next? In fact, let's just consider, before we go down that path, how this might be done using our formulas for constant acceleration. So what we're going to do is resolve things only in the vertical direction, and so we've got to work out the height it reached above the point of projection. Okay, now of course it's already resolved for us vertically, our initial speed, so that becomes the u component of our constant acceleration function when resolved perfectly vertically. But one thing you have to remember about using the formulas for constant acceleration, you can't take the origin to be anywhere else but the point at which constant acceleration comes into play. So when you're using formulas for constant acceleration, SAT, it always begins with the understanding that it's at the point of projection in this particular case. So we can set v to 0, we can set u to 50, the vertical component of our initial velocity, a to minus 9.8, and we can work out the distance it's traveled. It's not the distance it's traveled, the vertical distance above the sea level, it's this distance here. So it's the distance it's traveled above the point of projection, to which we then need to add 50 to get a final answer. So there's a little bit more work involved when using the formulas for constant acceleration. Okay, length of time it's in the air. Okay, obviously it could be, we've already determined, well, actually no. So it's not simply double the time it took to reach its maximum height. Why not? Because that, in fact, would give us the time it takes to return to the point of projection. So it takes double 5.1, 10.2 seconds to get to that, but of course it doesn't cater for the fact that it's got a further distance to travel before it plummets into the water. This is where vector calculus can be friendlier for you if you'd like. So what do we need to look at for length of time it's in the air? Okay, so what would be special about our position vector function? And if you were thinking about the j component, again, of our position vector function, you'd be right. So what would be special about the j component? If we set it to 0 and solve for t, then that's another way to, that's using vector calculus, that's a way to work out the length of time it's in the air. Because we set the origin at 0, it means when j is equal to 0, it's returned to sea level. So that's what we're going to do. We're going to set 50 plus 50t minus 4.9t squared to 0. Solving for t gives us two values, one of which is nonsense. In fact, that negative value actually has an interesting mathematical understanding, but there's a negative and a positive. We can reject the negative and focus only on the positive. I might just explain where that negative would come into play mathematically. If we're to continue the parabola into the negative side of for negative I, t equals minus 9.2. If we could travel backwards in time, reverse the process, it would lead to that x-intercept of the parabola, which is quite an interesting thing mathematically, but it's completely irrelevant in this particular situation. Now, how would you use your formulas for constant acceleration in this particular instance? Of course, because, as we said, everything begins oriented at the point of projection. That's when constant acceleration is at play, and we're only modeling vertical changes. S is 50 below the point of projection, so minus 50. U is the speed resolved, the initial speed resolved purely vertically, so the speed in the j direction. And of course, we've got our A. That's quite a simple approach to working out the time it takes to hit the water. Okay, so that's in fact reasonably neat using your formulas for constant acceleration. Okay, the distance out to sea is pretty easy. So we've already determined the time it takes for the object or the cannonball to hit the water. And of course, what can we do? We can substitute that into our I component of our position vector function. So these guys are aligning. So how far out to sea? How far is it in the horizontal direction? When time hits 11.12, it's of course 120 times t, which is 1.3 kilometers roughly. Now, how does that relate to constant acceleration, you might be asking? Of course, as we know, I'm just going to go back to our initial velocity vector. This is its component in the horizontal direction, which it's traveling at 120 meters per second at a constant rate in that horizontal direction because air resistance is ignored. So we've got the time it takes to return to hit the water. We know it's traveling at that constant speed of 120 meters per second. So of course, that leads nicely to just distances, speed times time, and arriving at exactly the same answer. So there we go. So we've looked at it from both techniques. Okay, the final part is determining the angle at which it's hitting the water. So there it is. The angle at which it's hitting the water. This is a very common question in projectile motion. I'd be surprised if you don't come across this several times in your study. Now, of course, determine the angle at which it hits the water is all about direction of travel. It's got nothing to do with our position vector function. I might just draw our position vector function is measured as follows. So as time's changing, so that's obviously, these guys aren't going to really help us. Of course, as time at 11.12 seconds, it's pointing to the point of entry in the water. But obviously that's not going to really help us determine our position vector function. So what we need to do is examine the velocity vector function, because that drives direction. So let's get into that. So we know it hits the water after 11.12 seconds, and we need to sub 11.12 into our velocity vector function. All right, and the angle at which it's projecting. So when we do substitute 11.12 in, we've got an I component and a J component. So just looking at the picture here, let me just grab my pen. We've got an I component, which should be positive, and a J component, which should be negative. So if I can use those components to work out this angle in here, which will be equal to that angle in there, the angle at which it's hitting the water, and you apply inverse tan, I should arrive quite neatly at a angle of incidence, an angle at which it's hitting the surface of the water. So here's a nice diagram for you. So when we do substitute 11.12 into our velocity vector function, we've got 120, as we know. It's traveling at that constant speed in the I direction, and 11.12 when I sub it in the J is about 59. Okay, but of course that's the angle I'm after, the angle of incidence with the water, which of course can be referred back to an angle inside the triangle, making up the velocity vector function 11.12, and we just use inverse tan. It's just as simple as that. So inverse tan the J component over the I component, we're ignoring the fact that it's negative, and we come up with an angle that will be equal to the angle of incidence, the angle at which it's striking the water. So hopefully that's all making sense to you. Okay guys, here's the final question of the session. A footballer is 30 meters out from goal and kicks the ball from an initial height of 1 meter above the ground. The ball takes half a second to travel through the goalposts at a height of 2 meters. So it's a situation where we're assuming the only acceleration at play is constant acceleration. As we said from the outset, we're assuming the ball isn't spinning, etc. It's idealized down to a single point, the center of the football, the center of mass of the football, yada, yada, yada. But I want you to see if you can answer these questions, find out the kicking speed, the initial kicking speed, and the angle at which the ball is kicked. So in other words, we started this session knowing v for initial speed and theta for the angle of projection, and we developed our expressions for velocity and position from there. We kind of have to work backwards in this instance. Feel free to use either vector calculus or formulas for constant acceleration. See how you go. Pause it now and look over the solution when you're ready. Okay, you're back. So I imagine you're ready for the solution. I've chosen to tackle this, in fact, using only formulas for constant acceleration. So the first thing is, I'm going to model the situation that the distance it's traveled in is 30 meters and the time it's taken is 0.5 of a second to get some information about the constant horizontal velocity. So we know capital V for our initial kicking speed, theta for the angle of projection. We know that V cos theta therefore is 30 divided by 0.5. Constant velocity must be traveling at 60 meters per second squared. So if we can get another expression involving V and theta, we're good as gold. Okay, let's go and do that. So what else do we know? We know initially it's 1 meter above the ground and the ball takes half a second and it's traveling at a height of 2 meters. So the change in displacement is of course 1 meter. So now we're starting to think of using our constant acceleration formulas purely vertically. So it's gone from 1 meter above the ground to 2 meters above the ground, change in displacement +1. It took half a second for it to travel in that way, and you're dealing with minus g is the acceleration, because it was zero acceleration for horizontal. It's an acceleration of minus g in this particular instance. Our initial velocity is, of course, our kicking speed, v, but as resolved in the vertical direction, it's v sine theta. Okay, so let's see, we've got S, we've got T, we've got A, we need U in this instance. So what comes to mind? That's right, S equals ut plus half at squared. We resolve to make U the subject, subbing all those values in, and you can see you get to 4.45 meters per second. Okay, so we've got V cos 60 equals 60 from resolving things horizontally, and V sine theta equals 4.45 resolving things vertically. So if we divide the two, our velocity rule, our capital V for initial velocity will disappear, we'll kill each other off, and we're left with tan. So we've got tan is equal to 4.45 on 60, enabling us to find theta is inverse tan of that ratio. Turns out to be 4.24 degrees, and that's we've in fact answered B first, the angle at which the ball is kicked. It's kicked at an angle of elevation of 4.24 degrees. Okay, what is the kicking speed? Obviously, we can replace, let's go to the simpler of the two. I'm going to go to this one over here. Let's go to V cos 60, let me just grab my pen. V cos theta is equal to 60. Replace theta with 4.24 degrees. And divide it into 60, and we actually get the kicking speed as well. All right, so you can see how neatly it can be done with the formulas for constant acceleration, but just know S for displacement is always at the point of projection, whereas in vector calculus you can, as we saw before, start the origin at a more convenient point for your problem solving. So I think those two examples highlight the different techniques, their pros and cons quite nicely. Okay, enjoy your frolic into the world of projectile motion.